In this video, I'm going to cover the process for the Unit 2, Section 1 practice on nuclear notation. So first in this video, we'll do a quick review of the atom. We'll then get into what nuclear notation is and why it's important. We'll go through a quick breakdown of each part of nuclear notation. We'll finish up with a couple of example problems and finally give you a chance for a self-check at the end. So first, let's quickly review the atom. Atoms, we know, are made of three different subatomic particles. The first are the protons. Those are our red particles there on the right. Next are our neutrons. Those are the blue particles on the right. And finally, we have the electrons orbiting around the outside of the nucleus. Those are the gray spheres orbiting around that nucleus. The mass of each I'm going to show below. Protons, we say, have a mass of approximately 1 AMU. Neutrons have a mass of 1. And electrons, we say, don't have any mass. That's not entirely true, but for our purposes, it's okay. It's okay to think of electrons as so small, they basically have no mass. The other thing we have to talk about is charge, and this is charge relative to one another. Protons have a positive 1 charge. That's the easy one to remember because of the P. Protons are positive. Neutrons have a 0 charge, or we say they're neutral. Again, we have that similar prefix, neutral and neutron. And then our electrons are -1. So really the electrons and the protons are kind of balancing each other out. So what is nuclear notation? Well, nuclear notation is a system that allows us to communicate a lot of information about an atom all at once. It gives us the chemical symbol of the atom, so what element it is. It tells us about the mass of the atom, the atomic number of the atom, and also the charge of the atom. It gives us all of this information directly. It also tells us the amount of each of the subatomic particles, the protons, neutrons, and electrons. And it does this indirectly. It doesn't say them outright, but you can figure out the amount of each from nuclear notation. So the important part is that nuclear notation tells us a ton of stuff all at once. So on this slide, we're going to do a quick breakdown of each part of nuclear notation. We're going to start here in the bottom left with this 26. And what this represents is the atomic number. And this is our number of protons. It's only our number of protons. It has nothing to do with the other two particles. This is kind of like the first half of our ID. This tells us what element we're working with. And furthermore, if we head here to the center of our nuclear notation with this Fe, this is our chemical symbol. This is how we abbreviate the element name. So Fe is an abbreviation of our element. This also only depends on how many protons our atom has. It doesn't depend on neutrons, and it does not depend on electrons either. So this 26 and this Fe, they are all about what element we're dealing with. If we head over here to the top left, this is our mass number, and this is the number of protons in our atom plus the number of neutrons. So it's how much our atom weighs or what mass it has. And finally, in the top right, we have our overall charge, and this is equal to the number of protons minus the number of electrons, although I do have one more way of figuring it out, and we'll talk about that in the next 2 slides. So this really is the breakdown of nuclear notation. We have 4 pieces of information that we have to kind of keep track of. In our first example, we're going to take that nuclear symbol and we're going to break it into a bunch of different parts. So first things first, because we know that Fe, and we also know that atomic number 26, we can look on our periodic table and find out that this element, its full name is iron, and we already have the 26, so we don't really have to use that. But we are going to take this name iron and just pop it in as the element's full name. Next, we know this 26 represents our atomic number, and we also know that the atomic number is equal to the number of protons. So those numbers should be the same. They are basically the same thing. Next, let's find our atomic mass. Well, on our nuclear symbol, we know that's the number in the top left. So our atomic mass is simply 57. Now we have to do a little bit of puzzling out to find our number of neutrons and our number of electrons. Let's start with neutrons. So what do we know about neutrons? Well, we know that the neutrons are related to the atomic mass. Our neutrons plus our protons give us our atomic mass. If I plug in the information I know, I can see that the atomic mass is 57. We know that from our table and from our nuclear symbol. We know my number of protons is 26. So some amount of neutrons plus 26 should equal 57, our mass. If we do a little bit of algebra, we can rearrange this to see that 57 minus 26 gives us our number of neutrons. And once we solve that, we'll see that we have 31 neutrons. Now let's do a really quick check. Would 31 neutrons plus 26 protons give us an atomic mass of 57? It would. And really, as long as you know the atomic mass and one of these two pieces, you just have to find the difference to find that other piece. But for us, we know that our number of neutrons is 31. And now we have to find this number of electrons. So what do we know about electrons? Well, we know that the charge of our atom is equal to the number of protons minus the number of electrons. We could set up our equation and say that positive 3 is equal to 26 minus the number of electrons we've plugged in for the things that we know. But I actually do this a different way. I like to look at this positive 3 and say, okay, I know that I have more protons because this is positive. And I know that specifically I have 3 more protons because it's a plus 3. So if I head over here to the right, I know I have 26 protons, and I know there are 3 more protons than there are electrons. So I would expect this number of electrons to be 3 fewer than my number of protons. However, if we head back to the equation, we can check this logic. Using some algebra, we can get electrons by themselves, and we know that 26 minus 3 equals our number of electrons, and this gives us 23 electrons. So let's check. Does that make sense? Well, we know the charge is positive 3, and we indeed have 3 more protons than we do electrons. So this makes sense. So in this example, we went from the nuclear symbol to a lot of the pieces. In our next example, we're going to take just a few pieces of information and build that nuclear symbol. So let's see what we know first. We know the number of neutrons, the number of electrons, and the atomic number. The first thing I'm going to do is say how many protons I have, because I know that the number of protons is equal to the atomic number. Next, let's find that chemical symbol. Using our periodic table, we'll look for the 34, represented by our atomic number, and we'll see both the symbol Se and the name selenium right here on our periodic table. Let's put that information into our example. First, I'll put that Se in the middle of my nuclear symbol, and then I'll put selenium in that element name. Next, we know the atomic number, so we might as well put that in our nuclear symbol on the bottom left. And now we're kind of stuck. We still need 2 pieces here in our nuclear symbol, the mass and the charge. Let's find mass first. We know mass is equal to the number of protons plus the number of neutrons. In this example, it's a little more simple. We have 34 protons and 45 neutrons. And when we add them together, we'll see the atomic mass is 79. And we can put that both here in our table and here on our nuclear symbol. Now it looks like we're almost done. All we need is that charge on the nuclear symbol. I'm going to talk this out logically first. I can see, comparing my number of protons and number of electrons, that I have 2 more electrons than I do protons. Since electrons are negative, I would expect this to have a charge of negative 2, because there's 2 more negative electrons. But let's use the equation. Charge equals protons minus electrons. Charge equals 34 protons minus 36 electrons. And so our overall charge is indeed -2. And I'll put that here in my nuclear symbol. So here, this is a self-check, and I've given just enough information that you can fill out the whole table. You'll have to do things a little bit differently in this one, but at the same time, you have all of the information you need. I would suggest you start with this element name and then work your way across the table, but you will have to jump to a couple different spots as you go. Go ahead and pause the video now and try to solve this. Okay, now that you have your answer, check against what is on screen. This is what you should have gotten. I hope that this helps you understand nuclear notation and how you are able to construct it and use it.